Welcome back, scholars. In today's video, we're going to begin looking at the concepts and theories surrounding the roots or zeros of polynomial functions. In past units, we've solved quadratic equations, which really means that we're finding the inputs where the equation f of x equals 0 is true. That's exactly what we'll do with polynomials. Let's get started. Throughout this lesson, we're going to be referring to the roots or zeros of a polynomial. Note that when we're discussing the graphs of polynomial functions, we display a domain, an x-axis of real numbers. Recall that the zero of a polynomial, p of x, is the solution or root of the equation p of x equals 0. Since the axes of the xy plane represent real numbers, we interpret zeros as x-intercepts only when those zeros are real numbers. In other words, we're not going to see complex roots on the graph. Here's a comparison to look at. We have two quadratic functions. In red, we have f of x equals x squared minus 4. And in blue, we have g of x equals x squared plus 4. Note that the two roots of the red function, x squared minus 4, appear as two x-intercepts. The blue function g of x also has two roots or zeros. However, they are not x-intercepts. Let's define the fundamental theorem of algebra. Now, as the name implies, this is a critical or foundational theorem that is really the basis of a great many algebraic principles. Suffice it to say, this is absolutely one you should know. So, what does it say? It says that every polynomial function of degree n greater than 0, so in other words, the degree is 1 or greater than 1, has at least one 0 in the complex number system. Let's break this definition down just a little bit more, specifically the phrase complex number system. Recall that the set of complex numbers contains both the real and imaginary numbers. We express a complex number using the form a plus bi, where a is the real term or the real part and bi is the imaginary part, which is really just units of I, which is defined as the square root of -1. So for example, going from left to right, we have 1 plus 2i, a complex number consisting of a non-zero real and imaginary part. We have 1 plus 0i, which is a purely real number, and we have 0 plus 2i, which is a purely imaginary number. All three of these examples would be considered numbers in the complex number system. So let's take that back to our fundamental theorem of algebra. When we say at least one 0 in the complex number system, we're acknowledging that the roots or zeros of a polynomial are complex numbers which include both the real numbers and imaginary numbers. All right, let's break down this theorem even further. In various textbooks or online sources, you may see this theorem stated alternatively as the NZeros Theorem, which says that a polynomial function has exactly n zeros where n is the degree of the polynomial. So this is the fundamental theorem of algebra, or another way of expressing the fundamental theorem. So essentially, a polynomial of degree 3 has 3 roots, a polynomial of degree 5 has 5 roots, and so on. There's a few additional features or caveats we need to talk about though. First, zeros are not necessarily unique. In other words, a root could be repeated. The first example of this you saw in your algebra careers was the case with a quadratic function with its vertex positioned on the x-axis. This was referred to as a double root, which we now know is the same thing as a root with a multiplicity of 2. That brings us to point 2 here, which is that each root or 0 must be counted by its multiplicity. So back to that quadratic function with one unique x-intercept. We would count this root twice because written in factored form, we find that this function's root has a multiplicity of 2. The quadratic function, of course, has a degree of 2. The last point here applies to both imaginary and irrational roots. We always find that if a plus bi is a root, its conjugate a minus bi is also a root. In other words, these imaginary roots always occur as conjugate pairs. And this makes sense if you consider how we get these roots. Suppose we had the polynomial x squared plus 4 equals 0. When solving for x, we'd subtract 4 from both sides of the equation and then take the square root of both sides. When doing so, we'd arrive at x equals positive or negative 2i. In other words, we generate a conjugate pair of imaginary roots here. Similarly, if we had the equation x squared minus 5 equals 0, when solving for x, we'd add 5 to both sides of the equation and then take the square root of both sides. Now, we don't have an imaginary number this time, but we do have x equals positive or negative square root of 5. Again, we generate the conjugate pair, this time for irrational roots. All right, let's walk through a couple of the questions on your Go formative activity together. Look for the icon with the wrench at item number 11, and that's where we'll begin. For number 11, we're looking to write a polynomial equation in factored form. We are told that f of x is a cubic polynomial, that means third degree, with zeros at -3, 1/2, and 1. We're also told that there's a y-intercept at y equals 1.5. We'll start by writing a general factored form equation. The degree is 3, so we know we'll need 3 sets of factors because the fundamental theorem of algebra says that the degree of a polynomial is equal to the number of roots. I also need to account for the leading coefficient or dilation factor of the function, and we generally use a for that. So I've got f of x equals a times 3 sets of empty factors. Now let's fill in those factors. I'm told that -3, positive 1/2, and 1 are factors. So this will correspond to x plus 3, 2x minus 1, and x minus 1. Let's talk about this middle factor, 2x minus 1. This one could also be written as x minus 1/2, but generally we like to express these factors with integer constants, so we've instead made this 2x minus 1. Now, we have a general polynomial, but we need to customize this equation to fit the given information. Look at the y-intercept given, and now we'll solve for a. I know that when x equals 0, f of x equals 1.5. So let's substitute 0 for x and solve for our dilation factor a. It looks like we'll end up with a equals 1/2. So our final equation will be f of x equals 1/2 times x plus 3 times 2x minus 1 times x minus 1. Let's look at number 12 now. We are writing the equation g of x, and it's a quintic polynomial. That's a 5th degree polynomial. We are given zeros 1 and 2 with their multiplicities, and we're given a y-intercept here. I know this is a y-intercept because the input is 0 and x equals 0 at the y-intercept. Just like before, I'm going to set up a general equation, and I'll make room for my 2 given roots. This time I'll have x minus 1 and x minus 2, but their corresponding multiplicities of 3 and 2 will need to appear as powers for each of these factors. For x minus 1, I'll have the third power, and for x minus 2, that will be the second power. Next, I'll substitute x equals 0 and solve for my dilation factor a. This time I get a equals 3. So altogether, I've got g of x equals 3 times x minus 1, quantity cubed, times x minus 2, quantity squared. Let's double check that I have a 5th degree polynomial based on the sum of the multiplicities. 3 and 2 makes 5, so I do have a 5th degree polynomial. Let's also verify that I've accounted for all of my roots. According to the fundamental theorem of algebra, a polynomial of 5th degree will have 5 roots when I include multiplicities in that count. And yes, I do have that here. Let's look at one more together, item number 13. We have h of x, which is a cubic polynomial with zeros 1, square root of 5, and negative square root of 5. There's that conjugate pair of irrational roots that we saw before. This time we're not given a y-intercept, so we'll assume that the leading coefficient or dilation factor a equals 1. A cubic polynomial will need to have 3 roots because its degree is 3. We'll set this up as h of x equals x minus 1 times x minus the square root of 5 times x plus the square root of 5. That wraps up our first look at the roots or zeros of a polynomial function. Next time we'll look at factoring as a method for finding the solutions to the equation f of x equals 0, as well as some additional theorems. See you next time.